What I'm going to talk about today is basically summarized in the outline. I will give a brief introduction of my work and my aims, and then I will give you a brief overview of the methods needed to perform the calculations that I would like to do, in particular looking at the chemical evolution of the universe and the cooling properties of the gas while it's forming structures at early times. And then I will show the main results about numerical simulations which have been performing looking at population 2 and population 3 stars, star formation rate, and GRB hosts as main applications. So let's get started with the goal. The goal of my work is to understand the primordial structure formation and the transition from the primordial stellar regime to the subsequent stellar regime. The primordial stellar regime is supposed to be characterized by stars which are born in a pristine environment. This means that the collapsing gas can cool only via hydrogen and hydrogen molecules, which leads to stellar masses which are probably quite high, usually up to hundreds of solar masses. These population 3 regimes eventually ends up polluting the medium. The next generations will probably form in pre-enriched environment. And these pre-enriched environments are characterized by higher metallicities, which allow the gas to fragment to smaller scales and to form present-day-like stars. And these two regimes, POP2 and POP3 regimes, are interesting also from the GRB point of view because they can be different progenitors for GRB events. More in detail, I would like to answer a number of questions, some of which are summarized here, as you can see. So questions as what is the formation epoch of the first objects? What is the role of molecules and metals in the early universe? How relevant is the population 3 regime in comparison to the whole star formation rate, to the whole star formation in the universe? What are the effects of different initial mass functions on the star formation rate? What are the effects of other parameters like the underlying matter distribution, Gaussian, non-Gaussian matter distributions at early times? What are the effects on cosmic ionization, and so on? So, I mean, these are many questions. I will try to give some answers, probably not exhaustive answers, but this is basically the main line of research which I'm following at the moment. In order to understand and to answer all these questions, we have to study carefully the chemical properties of the cosmic medium during the whole cosmological evolution. And usually I'm doing that using and implementing also n-body hydrodynamical simulation, including also chemical and stellar evolution. In general, we know that the universe is flat and it expands at a rate which is roughly 70 kilometers per second per megaparsec. The cosmological parameters which have been derived so far are listed here. These are the latest Planck results, which are compatible with a total matter density of the universe equal to 1. And 30% of this matter is in a dark form. The rest is in a form which is known as cosmological constant or dark energy. The baryonic matter, which is basically most of the matter which we can see from Earth, consists only of a small fraction, so about 4%. And nevertheless, we still have to understand the properties both of dark matter and dark energy, but also of the baryonic fraction, which has still many open issues. In general, when you perform calculations, the results are not extremely sensitive to the detailed initial parameters, and so people sometimes just use the so-called standard cosmology, which consists of an H naught equal to 70 and omega lambda omega matter equal to 0.7, 0.3, just for simplicity. Then once we have understood that the universe is flat and is expanding at the given rate, we need to understand how cosmic structures originate in such expanding cosmic space. The idea is that the present-day structures derive from the growth of initial matter perturbations, which were generated at early times during the so-called inflation epoch. So while the universe is expanding, these small perturbations can start growing and attract matter and collapsing material. In this growing of the matter perturbations, the gas can infall and cool and eventually fragment and form stars and galaxies. That's the main idea behind our cosmological picture. However, it's not obvious that, that the gas will definitely fall into the dark matter potential well and cool, because in order for this to happen, it's necessary that some properties, like the cooling time of the gas, should be smaller than the free fall time of the gas. The cooling time of the gas is basically the typical time scale at which the gas emits and radiates energy away, and is a strong function of temperature, as you can see here, and of density and composition, because a medium with different chemical abundances can have different atomic or molecular transitions and radiate energy in a different way, more or less efficiently. Obviously, at early times we expect to have low or no metals at all, and we expect to have a gas cooling dominated by the molecules. The main molecules which we expect to dominate at early times are H2 molecules, basically hydrogen-based molecules, because the hydrogen is the only element that we have besides helium anyway, but the hydrogen is the main element that is available for cooling of the gas. After the first star formation events and the pollution of the universe, we will also have additional cooling from metal transitions, which will enhance the cooling capability of the gas. This change in the chemical composition is sometimes called as chemical feedback.
What redshift is happening?
Well, this depends, in general, this depends on the regions. In average, this depends at redshift higher than 10, definitely higher than 6. So we are in the first giga year of the universe. So we are talking about 1 or half giga year after the Big Bang. Obviously, if you want to understand how this works properly, you have to follow a molecular evolution, chemical evolution, stellar evolution, which injects metals into the surrounding mediums in different places of the universe, and you have to implement it into some kind of numerical codes which can handle all these calculations.
Let's say someone we have evidence for quasars at redshift of...
For?
There is evidence for quasars at redshift of 8, something like that. So if someone detects quasar at high redshift, the prediction is that they should have vastly different properties.
The prediction is that? Sorry.
Should have, because, you know, the non-quasars have metallicity, which is similar to what we know, just from the lines and everything. So if there are quasars at redshift of, I don't know.
Well, I will show later that the metallicity evolution is a strong function of the environment. So you can start polluting the medium already at redshift 15 and to have rather high metallicity locally at redshift 15. But of course, if you move away from this early star forming region, the metallicity will drop down. So this depends on the environment as well. But I will talk about this more in detail later. I mean, the next few slides. So this is just a sketch of what primordial environments are expected to look like, at least statistically. On the left side, you can see a plot of the mass distribution of the halos at redshift 10. And you can see typical masses of the halos are about 10 to 7, 10 to 8, 10 to the 9 solar masses. And then you have these tails at 10 to the 10, 10 to the 11. So this means that at redshift 10, the most common halos are expected to be basically what we could call small galaxies, dwarf galaxies, so rather small objects. On the right side, I show instead the virial temperature of some typical halos, in particular 1 sigma halo here, 2 sigma halo here, and 3 sigma halo here as a function of the redshift. And the horizontal line, the Cian line, I don't know if you can see, there is a horizontal line at 10 to the 4 Kelvin and one at about 300 Kelvin, if you can see it. So 10 to the 4 Kelvin is the temperature threshold for hydrogen cooling. So it's the temperature above which hydrogen is the dominant coolant of the gas. Below 10 to the 4 Kelvin, hydrogen is not efficient anymore because the energies are not high enough to excite the atomic levels. However, if you have molecules, you can cool the gas even below. And the main molecule which is expected to be found at this redshift is H2. H2 has a peak efficiency which is at around 300. So it's in this regime between 10 to the 2 and 10 to the 3 Kelvin, which means that even if your temperature is below 10 to the 4 Kelvin, if you have enough molecules, you can still cool the medium and form stars via molecular cooling. In general, people talk about these two different regimes as H-cooling halos because their cooling is dominated by hydrogen, and this is true for halos whose virial temperature is higher than 10 to the 4 Kelvin. And then on the other side, we have the so-called H2 cooling halos, whose virial temperatures are around below 10 to the 4 Kelvin. And in the primordial environments, we expect to have mainly H2 cooling halos. So if we want to understand early structure formation, we have to understand hydrogen chemistry at early universe. So we have to follow H2 evolution at in the early universe. In general, we have, as I said before, we need to follow not only gravity and hydrodynamics coupled to molecular evolution and metals, and we need to do that because molecules are supposed to determine the very first structure formation events. The metals are instead supposed to influence the subsequent structure formation, so the next generations of stars which will be born after the pollution from the first objects. And then we have to also consider stellar evolution, because stellar evolution is an important ingredient as it determines basically the time scales and the yields of metal pollutions. In fact, stars with different masses have different lifetimes and different metal yields. So having a star of 10 solar masses exploding at, forming at a given redshift is different than having a mass of 1 solar masses at the same redshift, because the delay in the pollution events will be much longer in the latter case. So what I've done is just in the past few years was just to implement this molecular evolution and metal evolution, stellar evolution in gadget. I mean, I did my PhD in Munich in Garching, so I'm mainly working with gadget. I have been mainly working with gadget. This is an example of the cooling function which you can implement in the code. And the cooling function here is plotted for primordial environment, this dotted line. You can see at around 10 to the 4 Kelvin, you have the hydrogen peak, which is led by hydrogen collisions. Then at almost 10 to the 5, you have the helium peak, while at larger temperature, you have the Bremsstrahlung emission. At lower temperature, 10 to 3, 10 to 4 Kelvin, you are instead dominated by H2 cooling. The calculations of this H2 cooling have been performed by assuming a fraction of 10 to the minus 10 to the minus 5. Of course, in different environments, you will have different fractions, and so this line will be shifted up and down accordingly. If you include metals, here is an example of the cooling function for different metallicities. The picture can change quite dramatically, both at high temperature here and at low temperatures here. And the main contributors to the cooling at low temperatures are essentially fine structure transitions from basically LS coupling. The main transitions are expected to come from carbon, oxygen, iron, and silicon, simply because these 4 elements are the ones which are mainly produced by stars, and therefore you should care more of these rather than other elements. And then you can finally, once you have implemented all this machinery, you can finally perform some simulations and some calculations. And in particular, I have studied, you can study if you want, the transition from the primordial POP3 and the following POP2 regime according to the so-called critical metallicity. The existence of this critical metallicity is related to the fact that different stellar populations have different IMFs. So if the metallicity is very low, then your IMF is supposed to be top heavy, or anyway you are supposed to form massive stars. If the metallicity of the medium is higher, you are supposed to form low mass stars, because metals can enhance cooling and help with the fragmentation of the protostellar clouds. The calculation of this critical metallicity, however, is quite complicated because, and uncertain, because there are parameters which we do not understand completely. For example, there are some atomic parameters which are missing, and we also don't know what is the fraction of metals depleted into dust, which do not contribute to gas cooling. Nevertheless, we have some ranges in metallicity. This critical metallicity can range between 10 to -6 and 10 to -3 solar. So we have a huge range of about 4 orders of magnitude or so, according to different authors. However, when you perform these calculations, you can take into account this as an external parameter, and in fact, here there are a short summary of the simulations that I have done over the last few years. So lambda CDM cosmology, molecular metal chemistry. I have assumed the critical metallicity for POP2, POP3 transition in this range, but I will show later that the fact that we don't know very well this critical value is not crucial for our understanding of the early universe. And then you can also check what happens if you assume different POP3 IMFs, which is also an unknown function, or different dark matter distribution, and so on. Here, I just wanted to give you a brief idea of what the primordial universe looks like. So basically, here you are on 500 kiloparsec scales, a redshift 10. So you have the first star-forming region, which are these bright, cold spot here, like this. These are all structures which are just forming, and the gas in this region is basically cooling and collapsing. Now, once you...
So yellow means normal metallicity and green means hydrogen or something?
Well, this is only primordial gas. So here you have only more dense and less dense material. These filaments and knots are very dense material, while the other is more rare, more diffuse gas. This is a redshift 10. While over cosmological times, these will form stars, and the stars that you will form, for example, on 100 time scales, will determine supernova explosion and metal pollution. So supernova explosion means that the temperature of the gas can increase because the stars hit the medium, and you start having a kind of brighter and brighter universe, and hotter also universe. And here you can also see quite well also the shocks determined by early structure formation and supernova events. And the gas is usually heated above 10 to the 6 Kelvin or so. And then you can check for the metallicity evolution. This is just for metals. Metallicity is related to star formation events. So as soon as first stars explode, they spread metals in the around, and here you form the first heavy elements in the universe. So these are the very first episode of star formation, which then sum up, and you have more and more metals in the universe. And you can do that by looking at different elements, for example, oxygen, iron, and if you look at the oxygen and irons simultaneously, you can see that usually oxygen, which is mainly produced by supernovae type 2 or peri-instability supernovae, is formed earlier than iron. Here there is no iron, and now there is some iron, so there is a time delay in the formation of iron over the cosmological epoch, simply because iron is mainly produced by supernovae 1A, so you have to wait longer before having iron in the universe. I mean, you can follow this kind of evolution for different species. So I have a number of, we have implemented a number of species, and only oxygen and iron are plotted here just for sake of simplicity. Here are some results. On the left panel, you see the metallicity maps of the metallicity map of these at redshift 13 and 11. These two metallicity maps are at the same redshift, but they have different, they refer to simulations with different critical values, 10 to minus 3 and 10 to minus 6 solar. So as you can see, there are some very small, tiny differences, but they are not extremely huge. And this is due to the fact that early star formation events are able to pollute the medium at levels higher than the critical level. So you are already at a fraction of I mean, here you are at 10, you can get up to 10 to minus 2 solar already. At later times, you also have some small differences, but I mean, as you can see, they are not so, yeah?
You said that iron is contributed mainly by type 1A,
Mainly.
but I mean,
There is iron also in other, if you take the yields, you have iron also in
I thought that people claim that there is a delay, you know. Type 1A don't follow star formation and things like that.
Yeah, but you follow, you form stars, and then you follow the time scale for these stars, and wherever they are, at some point they explode, and you have.
So early.
Sorry?
So early.
So early because iron is not only due to supernovae 1A, but you have iron also in peri-instability supernovae, supernovae type 2. So you can still have some tiny iron. Even a redshift slightly before 6, yes. But you are expected through. You expect to have a lot of iron below redshift 6, so after 1 gigayear. But still, you can have some iron earlier. If you take the stellar evolution models and you follow the time delay distribution, the time delay distribution is not an average, just a broad distribution, which go from 10 to 8 to 10 to 10, and with a peak around 10 to the 9. So it's not unlikely that you will have iron before redshift 6.
I just want to make sure I'm understanding this. This is metallicity, which essentially looks like star formation.
You mean looks like
that map is metallicity.
Yeah.
Okay. It is, but that essentially looks like star formation.
I mean, metals are spread around the star forming region, so yeah.
Okay, and it also essentially looks like mass.
Mass of what? Of stars?
Just density of mass.
I mean, you will have more metals in more clustered regions and less metals in the diffuse regions.
Not metals, but mass.
By mass, yeah.
Just mass. Just
metallicity.
Just dark matter and hydrogen.
No. This is gas mass. So the metals are associated to gas mass. Okay, so for each point...
But the gas mass looks the same as the metal map, which looks the same as the star forming
exactly.
map.
The densities are different. So if you take the gas mass, you will have some filaments going like this. And around the densest region, you will have some metals.
You'll find there's a bias from the metallicity to be in the more dense region more than linear with mass, because you get more massive stars when there's more gas to start, and that makes more metals more quickly. And so
the part that I don't understand is you have this phase transition. You have a phase transition when you go below, I forget what temperature, and you go to molecular cooling. So why aren't these, and you have much cooler small concentrations, small halos. So why don't the small halos always collapse first?
Because a halo which is small now, or which is big now, was smaller earlier. So this means that if the halo is small, it doesn't mean that the gas had time to radiate away the kinetic energy and to cool. So you have to wait a bit, let's say 10 to 7, 10 to the 8 years. During this time, the halo also grows a little bit. And so you have this kind of balancing effect. And usually you will have, these are all small halos in the sense that they are all below, say, 10 to the 9 solar masses. But this doesn't mean that the 10 to the 6 halos are forming stars earlier. Usually you will have stars first in 10 to the 8 solar mass halos, and then 10 to the 6 or 10 to the 7, something like that. Because you still have to include the time delay due to the gas cooling to radiate away energy. So, and while the gas is radiating away energy, the halo grows, right? So it's a balancing process. Yeah. At the end, you can get the overall star formation rate density in the universe, which is this line here. And you can look for the POP3 contribution. The POP3 star formation here is these 4 lines plotted for the 4 critical metallicities which I mentioned. And if you divide these lines by the total, you get the fraction of POP3 star formation rate, which is going basically from unity, a redshift say 16 or so, and then it's going down to less than 10 to minus 3, a redshift 10, 11. So you expect to have a rather fast transition from POP3 to POP2 star formation regime. And this transition is led essentially by the metal yields of early stars, which are rather high. So basically, the first generation of stars spread around in the universe a lot of heavy elements, and the next generation is already present-day-like. You have some differences, some small differences according to the different critical metallicities, but as you can see, they are all lying within a factor of a few, less than 1 order of magnitude anyway. And then here are some phase diagrams. X-axis is density, y-axis is temperature. The plots is done only for metal-rich material. The metal-rich material is, of course, found first in high-density region and low-temperature region, which is this one. But then later, as star formation goes on, you pollute wider and wider areas, and therefore you start polluting also lower-density regions, which are slightly higher temperature, as you can see here. And then eventually you even get to almost void regions. Like here, for example, where you are at between 10 to 4 and 10 to 6 Kelvin, and you are at densities which are some orders of magnitudes below the critical densities. Interestingly, you can quite see this, the whole thermodynamical path followed by the gas while it's collapsing, because you might think of this plot as a time sequence, where the gas is initially at temperature, at low densities, while it's falling into the dark matter potential wells, it's shock heated, which means that the temperature increases up to 10 to the 4 Kelvin or so. 10 to the 4 Kelvin means that you have strong H cooling, which doesn't allow the gas to be heated at higher temperatures. So the gas gets stuck at 10 to the 4 Kelvin or so for a while, as you can see here. And this a while means up to 10 to the 8 years, so 0.1 gigayear. And eventually, the gas becomes dense enough to form a lot of molecular hydrogen, and the molecular hydrogen drives this fast cooling phase here, which eventually leads to star formation. And basically, in general, the whole metal pollution process is I mean, people say that this is a kind of inside-out mode of metal pollution. So you start from the innermost regions and you pollute down towards the outermost regions. And you have a similar statistical analysis here, where I show the joint probability distributions of metals as a function of over densities, and these are the conditional probability distributions. And as you can see, you have most of the probability distribution most of the probability is at higher densities, and also you have this bump here, which is in a lower density medium. The delta, the over density is 10 to the 2 here. So this means that you are polluting a lot of unbound material from first star formation events. So basically, the gap of metals here is mainly due to the fact that the material produced here is ejected outside from the halo, and then eventually it stays there, or if the material is ejected shorter away, it cools immediately and goes back into the central regions.
Can I ask a question to the previous slide? There was some limit imposed on the density.
This.
Yes, this is a shortcut.
Yeah, this is the shocks. These are the shocks due to star formation events, which hit the surrounding medium to 10 to the 4 Kelvin or higher immediately, instantaneously, as soon as you form stars. So these are basically star-forming, shock-heated star-forming
So there are no chance to get clumps denser than 10 to the power minus 22 or with something or whatever?
Well, I mean, this is what's, I'm sorry. Okay, these overdensities, let's say that when you convert into overdensities and physical overdensity, you get overdensity of 10 to the 8 or so. But this is also due to the resolution limit of the simulation. So, I mean, you must be careful with this, okay? Yeah, and then you can look better at the radial profiles of halos to see where POP3 material is located. So I took basically the first star-forming halo in the simulation, a redshift 15, 13, and 11. So, and I plotted the contribution from POP3 and POP2 material. The POP3 material is the dashed line. The POP2 material is the solid line. And as you can see, as time passes, the POP2 material is basically polluting the innermost region, while outwards it's the POP3 regime which is dominating. And when you go further on with time evolution, you almost see that the innermost regions are completely polluted, while the outermost region in the outskirts of the halo, there is still some possibility of having a POP3 material. But this shows very nicely how metal pollution proceeds within the halo. So basically from redshift 15 to redshift 11, you manage to get up to this vertical line, which is the virial radius. So these vertical lines here, here, here are the virial radii of the halos, of this halo at different times. And so in a few 10 to the 8 years, you can enrich the universe above the virial radius. So you can inject metals in the IgM, basically. And then you can play a little bit with the parameters and see what happens if you change, for example, the population 3 range. Because the population 3 range is a quite debated issue. According to some works, and according to what I have assumed so far, the POP3 stars are expected to be between 100 and 500 solar masses. Such massive stars can explode as pair instability supernovae when their mass is between 140 and 260 solar masses. In this range, they can eject a lot of methane and pollute the medium. However, if you look at different works in literature, you can find different ranges. And for example, I have checked what changes if you go to a standard salpeter-like POP3 IMF, which is this black line here, compared to the top-heavy IMF, which is the red line here. And you can see that the contribution to the star formation rate is almost within a factor of 3, let's say 2 or 3. So there are IMF dependencies, but they are not so heavy, not so strong. The green line is an intermediate IMF, 800 solar masses, which I took when it was suggested that there was the possibility to form 10 solar mass stars in reionized gas. So if by chance you have pristine gas, which is for some reason reionized, you might form stars with 10 up to 40 solar masses. And also the ratio, the POP3 contribution is still, again, going down with redshift within a factor of, say, 3. Similarly, you have some degeneracies with the supernova range, mostly for primordial stars, because if you look at some paper like the one by Hager and Woosley or Woosley-Weaver, they wrote a bunch of papers in which they claim that the supernova range might be from 40, the supernova range might be from 8 to 40 solar masses, but in some other works they claimed that the supernova range could be from 8 to 100 solar masses. So there is this mismatch between 40 and 100 solar masses, which cause degeneracies. The authors didn't come up with a real explanation of why they get these discrepancies. But anyway, also in this case, you can have effects from the supernova range by 1 order of magnitude. These effects are higher because the supernova range, the metal pollution is relevant to the upper limit of the supernova range. If you assume that the first supernova which explodes and pollutes the medium is at 100 solar masses, this means that this star has a lifetime which is much shorter than a 40 solar masses, and then it starts enriching earlier, which means that everything in the universe takes place earlier. And then you get this line here, for example. Then you can also change the yields table, but the yields table are quite irrelevant because these different plots here, the dots here, refers to different yields table when the amount of metals ejected reaches the threshold, the critical metallicity. And then you can see that these cyan dots and blue dots are very close to each other, so there is not a strong dependence on the yields table. What matters is the total amount of metals that you manage to put into the universe. So, in order just to summarize, I wrote this sequence of implications. So basically, all this can be understood by the fact that if you have larger POP3 masses, then you have shorter stellar lifetimes, hence earlier metal enrichment and shorter POP3 epoch. Okay.
There's some subdivision of the POP3 population.
Yeah, POP3.1, POP3, yeah. Yeah, but I mean...
what's the explanation? They might differ by the heaviest possible mass of what?
No, it's just a matter of metallicities. Some people... so far I have assumed the POP3, everything with a metallicity below than the critical. Then you can distinguish those star-forming regions with a metallicity below the critical but higher than 0, or those with metallicity equal to 0. And then you have POP3.1 and 0.2, but no relevant difference at the end. It's the same, doesn't matter so much. Because at the end, the critical metallicity is so small that 0 or crit is almost the same.
Right. So my question is, how did you come up with that the early formation rate ramps up between a redshift of 15 and 16?
From the simulation.
From the simulation. What you're assuming is the dark matter simulation, the lambda CDM simulation, yeah. and then how do you get the gas? How do you calculate how the gas?
You put the gas in the initial conditions together with dark matter at ratio 100, and then you compute both hydro and body from ratio 100 down to ratio.
And the cooling of the hydrogen.
Cooling H2. Yeah.
Right, and then you're assuming how the H2 forms, right?
No. I'm following the equation, non-equilibrium equations. So basically, I have a set of equations which I didn't show here, but you have a set of 20-ish equations, or chemical equations with rates, and you can compute the time derivative of the abundances of each abundance, and so you can follow the formation, the destruction.
So you will predict that there should be GRBs out to a redshift of 15.
I'm coming to the GRBs, yes, POP3 progenitors. I mean, with POP3 progenitors. Yeah. And this is. I tried to compare the simulations to the specific star formation rate to understand how simulations are going in comparison to data. And you can see that these are the data. The safest one are expected to be this one. These one are now outdated because they found a discrepancy in the data reduction. The simulation are suggesting a specific star formation rate which increases up to several tens, a redshift above 15. However, we have to say that at low redshifts we have a significant problem with reproducing a specific star formation rate with simulations, and this is probably related by the numerical limitations in performing large volumes. By the way, recently there were a few papers about from the Clash team which put some points around here, redshift 10, 11. By using lensed galaxies, they managed to estimate, very rough estimates, one galaxy at redshift 11 and found a specific star formation rate which is in this range, about 10 gigayear to the -1. And then you can check the luminosity function from the output of the simulation, and these are the luminosity function redshift 6, 7, 8, 9, with some data points which match quite okay the simulations, and a slope which is roughly equal to -2. Then finally you can use these simulations to trace the long GRBs and the properties of the host galaxies. In particular, what you can do is, for example, looking at the UV luminosity of GRB hosts, and here there are some lower limits, upper limits given by these different GRBs at different redshift. These are the known GRBs at redshift higher than 6, and it seems that these limits are compatible with our results, with our simulations. And you can, from the magnitude, you can also compute the amount of ionizing photons from these galaxies, and you come up with this picture at redshift 6. The red line is redshift 6, and the blue line is redshift 8. And also in this case, you have you can compare with the limits given by the observations, which are these vertical lines here. And the
you're speaking about ultraviolet in the rest frame of the galaxy.
UV, yeah. And then you can predict some statistical properties of GRB host galaxies. The star formation rates of these GRB hosts are expected to be around 10 to -1, 10 to -2 solar masses per year. And this magenta line is drawn by the observational limits, while the stellar masses are around 10 to the 7 solar masses. The specific star formation rate of these galaxies are expected to be between 5 and 10 gigayear to the -1. And then the metallicities are expected to peak around 10 to -2 solar. Interestingly, if you take this point, which is the only GRB for which we have a metallicity measurement, it matches with the peak of the distribution that we get at redshift higher than 6, which is either by chance or... I mean, it's interesting that at least we managed to match this point here.
Yeah, but you cannot evaluate fractions. How you done this?
No. I mean, these data points is not a fraction. It's just the metallicity. I mean, there is the shadow area, which is the metallicity. Yeah, I mean, this is only one. So the fraction is 1 here. But of course, yeah. No, you cannot evaluate the distribution. I agree. And then you can evaluate, compute further properties of GRB hosts, like UV metallicity evolution, which is redshift 6 and redshift 8, upper row redshift 6, lower row redshift 8. And also in this case, if you look at the UV metallicity, this is the measurement, so we are close enough. while in the other cases we have only the limits for the UV, we have no metallicity measurements. So the position here is just arbitrary. While if you look at the mass metallicity relation, you are also expected to see something like this, an increasing trend of metallicity with mass. And then you can look at the so-called fundamental metallicity relation by Manucci et al. But this relation was derived for isolated galaxies at low redshift. It seems that there is a kind of trend also at high redshift, but however, if you investigate further this issue, you will find outliers to this relation. And here, finally, you have the GRB rates for POP2 and POP3 progenitors. This plot is the GRB rate for POP3 progenitors. This is the contribution from POP3 progenitor going from 10% up to 1, which means 100%. And the contribution is roughly increasing with redshift. You expect to have 10% of GRBs at redshift higher than 6 coming from POP3 progenitors, while at redshift 10, 40% of the GRBs are expected to derive from POP3 progenitors. If you go at redshift 15, almost 100% are expected to come from POP3 progenitors. Similarly, you can look at the mass metallicity relation of the POP3 progenitors only, right? And at the end, you find that the POP3 progenitors are formed in a pristine environment, but when they explode, they enrich immediately everything, the surrounding regions above the critical metallicity, which is the vertical line, right? I think I'm out of time. I just want to mention, if you give me 1 minute. Okay. Yeah, just to mention that you can use the GRBs also in terms of non-Gaussianities and FNL, because I ran some simulation with different FNL parameters a couple of years ago, before the Planck data. I assume a 0, 10, 50, 100, 1000. And of course now the range is 0, 10, the one which is significant now, but at that time it was up to 100. And when you run these FNL simulations, you clearly see some differences at early times, maybe not so clearly, but later times show weak differences with FNL, mainly because gas evolution and thermal feedback, gas feedback is messing up things, and the baryonic matter forgets about non-Gaussianities at the end. But you can estimate the start from the GRB rate and put a point here, which is the observed point. This is the yellow line. The yellow area is the GRB rate computed for the FNL equals 0 case, so the Gaussian case, while the green line is the 1000 case, which was already ruled out at that time, and which we also compared with the Gaussian case. Up to redshift 6 or so, there is no great difference, but above redshift 6 you expect to see some differences, small differences actually. And we managed to put this number from the observed data, which is actually a lower limit to the GRB rate at redshift 6, which is consistent with the CMB predictions, but of course it's only a lower limit. But I mean, at least it's consistent. And this is these are the relative contribution of non-Gaussian models with respect to Gaussian models. And as you can see, at lower redshift, the differences are smeared out, while at higher redshift, you have some memories of primordial non-Gaussians. So I leave here my summary and conclusions, and thank you very much.